So last time, talked about planar graphs. So everybody knows what a planar graph is. So please, if somebody defines it real quick. So what is a planar graph? A graph that can be drawn on a plane without its edges crossing. That's what a planar graph is. Now, what did we observe about planar graphs last time? So there's a certain relationship that holds.
If the planar graph, or if a graph is planar and connected, then the vertex minus the edge minus the R.
Plus the regions.
Yes, regions.
Vertices
Thank
minus
you.
edge plus the
Equals to
regions.
plus the regions.
Yes, plus the number of regions is going to be 2. So there's a certain number of regions that a graph splits the plane into. So here you have these different regions, region 1, region 2, region 3, and you have this infinite region 4. So the number of regions, the number of vertices, and the number of edges of the graph are connected this way. It's pretty remarkable. Okay, that's one thing. We did make a few other observations about graphs. So which graphs were not planar? So this is an example of a planar G. Planar G. What is an example of a non-planar graph? We proved last time that certain graphs were not planar.
K5.
K5 is not planar. K5, not planar. What else is not planar?
I think if we have a complete bipartite graph, I'm not sure if that's what it's called, but like K33.
K33, 3 plus 3 vertices, that is correct. That's not planar. Is this graph planar though? K24.
Yeah, K4 is planar. Or
K4
we could,
is planar. But how about K24? So I'll let you think about this. It can also be drawn on a plane without the edges crossing. Okay, so it's not that difficult. You have to stare at it for a minute maybe, or whatever. Okay, so but these two graphs, K5 and K33, they are not planar. Okay, so these are two canonical examples of non-planar graphs. There's a stronger theorem to the effect that any graph that contains within itself either K5 or K33, okay, is going to be non-planar. And those are the only non-planar graphs. Okay, what was the relationship between the number of edges and the number of regions that we observed last time? We're going to use this result today. So today you'll be helping me to prove a few results. So we'll be all participating. Okay. So what else did we observe about planar graphs last time?
yeah, and what was the question? The relationship between edges and regions?
Yes, what are the relationships that we
okay.
observed last time? Yeah, it could be edges and regions, vertices and edges, whatever you remember from last time.
There was like something where planar graphs, the edges are less than or equal to 3 times the vertices minus 6.
Yes, number of edges is not going to be larger than 3 times the number of vertices in planar G.
Number of vertices is equal to degree of a region.
Sorry, one more time.
The number of the vertices is equal to degree of a region.
The number of vertices to the degree of a region?
Yeah, they are equal. For example, if there is a 3 edges, is degree of the region should be 3 also.
Oh yeah, the number of edges that surround the region is by definition the degree of a region. Is that what you mean?
Yep.
Okay, yes, that is correct. So we use the notion of a degree of a region to get some results. And what were those results that we obtained using those notions? This was one of them. So we're looking for a relationship among the edges and the vertices. This was one. Actually, this is the relationship that we need. How did we prove this, by the way?
Well, we found that, well, we said that each edge can border 1 or 2 regions. It can't be 0 or greater than 3 regions. Like an edge can't border 3 regions or more. And each region has to border at least 3 edges because it has to be like enclosed by 3 edges, right? So using that, we applied Euler's equation of V minus E plus R and made the inequality.
Yes, that's exactly right. So we observed that twice the number of edges was going to be at least, or so which one was it? So we plugged in. So we had this relationship that we rewrote this. Let me use a different color. So this relationship, which we multiplied by 3, because it was easier for us to not deal with the fractions. Okay, so twice the number of edges was greater. So we plugged in, so this is what we observed. So this is the observation that we made. And we plugged this into this formula to note that 3v minus 3e plus twice e is going to be greater than 2, right? So what do we get? First of all, there should be 6.
It should be 6.
And multiplied by 3.
Yeah, we multiplied both sides, right?
Yeah, so this should be 6. This should be 6. So from this, well, actually, let me not rewrite this because directly follows here. This is what we get. This is all that happened last time. Is this clear to everybody how we got this? So it was a bit of algebra. The main observation was this. Okay, we built a little bit of a matrix and counted the number of ones there. And with the help of that matrix, this is the result that we obtained. Then we used Euler's formula, which we proved earlier, to ultimately obtain this result, that if a graph is planar, it just simply can't have too many edges. What do we mean by can't have too many edges? More precisely, the number of edges should be smaller, or at least as many as 3 times the number of vertices minus 6. So that's the result. Now we're going to use, you're going to help me prove something today by using this result. So let's see what we're talking about today. Okay, so consider the following problem. So Temple University at the end of each semester needs to schedule classes, exams, let's say at Tuttleman in physical classrooms. And it faces certain constraints. The constraints are as follows. If a student is registered for 2 classes, then a final exam for those 2 classes cannot be scheduled at the same time, right? The final exams for 2166 and let's say 1068 cannot be scheduled at the same time if there is a student who's taking both of those classes, right? Does that make sense? Because the student has to take both final exams and you can't take them at the same time. So those 2 classes, if there's a student in those 2 classes, we're drawing an edge between those 2 classes. We have nodes in a graph that represent those courses, and we draw an edge if there's a student in both of those courses. And we build a graph like this. Now, so what is the problem? The problem is to assign time slots, the available time slots, to the vertices of the graph in such a way that conflicts do not arise for students taking those classes. So for example, if I have, because these 2 classes are connected, there's a student in both of these 2 classes have to be scheduled during different times. Cannot get the schedule at the same time slot. Makes complete sense, right? What the problem is. Now, you will look at this graph and say, what's the problem? I don't see any problem with this. I have 5 vertices in this graph, so 5 classes. I have to give final exams for all those 5 courses. And I have 5 time slots available. So just simply assign a time slot, a different time slot to each of these courses, and that's fine, and everything's fine. Well, that's correct, except that you want to avoid using those later time slots. If you do it this way, then there will be somebody taking an exam at 1 a.m. in the morning, and you like to avoid the sleepy students taking exams at that time. So you'd like to use the fewest time slots possible, right? So what is the fewest time slots that you can get away with here? Can you, okay, so you can certainly do it with 5 time slots, just assign a different color, different. So why did I say the word color? What do I mean by color? So what am I thinking about when I say assign a different color?
So each vertices in the graph will have different colors?
Yes, so these time slots, I'm thinking of assigning time slots as assigning colors to the different vertices. You could think it that way, about this that way. And the assignment must be such that no 2 adjacent vertices receive the same color, because an assignment of a color, just in our new language, corresponds to the assignment of the time slot. right? So for example, the red and green vertices must receive different colors. Now this guy can receive the red color here because there's no connection between these two vertices. Those two classes, those two exams can be scheduled at the same time, right? Maybe I'm using a different color, like for this one, maybe. Okay, don't know why, this is not the most optimal assignment. Maybe I use the 4. You can get away with 4 colors, but you can do better than that, right? What's a better assignment? Can you get away with fewer than 4 colors? 4 times. So this means that I can use up 4. I don't need all these 5 slots. I can get rid of the last time slot. Don't have to assign it. So I can use up 4 of these time slots. Can I get away with fewer than 4?
Yeah, in the chat, Jesse said that the black dot could be a green dot.
Yes. Yeah, you can this can be green, or the other can be, I don't know, any way you'd like. Yeah, I guess I shouldn't have erased that. This can be blue, let's say, right? So you can use a blue dot or a green dot, either way. So those can. So what happened here is you can get away with 3 of these time slots, right? The smallest number of colors that we get to use when assigning the colors to the vertices of the graph this way is called a proper assignment. Let's call it a proper assignment of colors. So let me give you definitions. Color assignment to the vertices is called, let's call it proper, if no 2 adjacent vertices get the same color in a graph. So it's clear, right? So this is definition. Definition 2. The smallest number of colors needed, the smallest number of colors needed to properly color the graph, to, let's call it proper color, properly color, proper color a graph, is called the chromatic number of graph, G. Graph G is called the chromatic number of the graph G. Notation is this, chi of G. So this is called the chromatic number of the graph. So what's the chromatic number of this graph?
Three.
Yeah, just by what we've argued. The chromatic number of this graph is 3. What's the chromatic number of K4?
Two.
Okay, so let's try to color it with 2 colors. Okay, this gets this color, this gets this color.
Oh, I'm sure K4, so it's all different.
Okay, so what's the chromatic number?
4.
Yeah, it's 4. You can't get away with fewer than 4 colors. What's the chromatic number of C5?
3.
Okay. What's the chromatic number of C4?
2.
Do people see this? Do people see this? So that's the definition of what a chromatic number is. And you see the context where it just came up in resource assignment problems, airline scheduling problems. This is the example that we just gave as assigning limited resources. It's just the constraint of limited resources in the assignment problem of time slots to classrooms and so on and so forth. So these graph coloring problems come up in a variety of contexts, but we'll stay on the abstract level because we'll try to stay as general as we can. Let me ask you this. So what we'd like to talk about today is coloring maps. Okay, so let's take the map of, let's say, of the United States. Now let's take this map to get started. So what we have is different regions here. You see these lines are the boundaries. See the boundaries? The idea is to assign a color to each one of those regions in such a way that no two bordering regions will receive the same color, right? So this is the so-called map coloring problem. What does that mean? You want to color a map like the map of the United States in such a way that no two bordering states receive the same color. So you can tell that these are different states, right? So how many colors do I need? So let this be example 1. And here's an example 2. We draw a different kind of region here like this. So I'm coloring, notice that I don't have a graph yet. So I'll be asking you in a minute to associate this problem with the vertex coloring problem. So we're coloring maps here. We don't have this problem in the language of graphs yet. But the translation to the graph language is immediate, and you will give it to me in a minute. But for now, let's just see how many colors we need to color these regions. So please help me out. So how many colors do I need here? This region,
3.
1 color. This region, say, gets another color. This region, so I can get away with how many colors?
3. If you made this center, if you made the center of the third color and then made the outside every other.
Yeah, this assignment of colors works, right? Like this. Okay, so notice what I'm doing. I'm associating a region with a vertex of some graph. The graph that I'm associating this map coloring problem with is called a dual graph to this map. So this map has a dual problem, a dual graph, sorry, dual graph. Okay, this is the graph, this is some G, is dual G to this map, Okay, what's a graph G that's dual G to this? And what, by the way, what's the chromatic number? So what's the chromatic number of this G? You just told us it was going to be 3, right? Chromatic number of that graph G was 3. I want to know how many colors do I get to use? What's chromatic number is the fewest number of colors that I can use to color this region, this map properly. By a proper coloring.
Pick 4.
Okay, so yeah, so let's color this. Yeah, so you have this here. So let's write down a dual graph first. I have 1, 2, 3, 4. So that's the dual graph. So the question we're asking then, what's the chromatic number of this dual? What is the chromatic number of this dual graph G? And you've already answered this question when I asked you what the chromatic number of K4 is, because the graph dual to this map is K4, as it turns out. Now it can be immediately seen when I just drew it. Here's a dual graph, and you just recognize it as K4. Say, okay, it's K4. And the chromatic number of this is 4. And indeed, you do need all these colors of these regions to be different. Okay, and it must be colored this way. So here's the coloring that we received. Here that we assigned to this graph. It's going to be that. That's the coloring of the graph. Okay, so that's the graph color. So the chromatic number is 4. Now, do you see that no matter how these regions are configured on a plane, because it's a map that's drawn on a plane or on a sphere, just not on a torus, as long as it's on a sphere or on a plane, the graph, the dual graph that I built out of it is, do you see that it's planar? It's going to be a planar graph, right? Do people see that? Do we have to argue this more clearly, why the graph is going to be planar? Because I'm connecting two regions. Okay, any two regions, I'm going to cross some boundary, right? These two regions, I'm assigning a vertex to each region. And when I'm connecting them, there's some boundary that's being crossed, right? This boundary will not be crossed by any other edge in the dual graph, right? Do people see this? Because this boundary belongs to these two regions only. Okay. Make sense? Okay, so the dual graph will always be planar. So when I'm asking the question, can the map of the United States be colored with, I don't know, 7 colors, 6 colors, 4 colors, 3 colors? What exactly am I asking here in terms of graphs?
I guess a way you could, well, never mind.
Yeah, no. What is it? What was the idea?
I was thinking find a state where the most number of states border it and see what the highest number of colors you can use, or the smallest numbers of colors you can use for that group, and that would tell you how many you need, the most amount of colors. But I don't think that works.
Okay, but I think it's a good idea. So, but let's first formulate the question. You're correct that it needs to be further sort of clarified, but the idea, I think, I think it's a good one. But let's see. Let's just explore this. So, what am I asking? So first of all, I'm building a graph that's dual to this map, right? So how many vertices will it have? So let's take the contiguous states here. Let's ignore Alaska and Hawaii for a second.
So 48 vertices.
It has 48 vertices. So what I'm asking is what is the chromatic number of this G? That's our question, right? What is the chromatic number of a graph that's dual to the map? What do you think the answer is? You may have seen this problem before in high school or even before. Do people know the answer to this? First of all, let me ask you this. Can I get away with 3 colors? Maybe it's possible to color the entire map with just 3 colors.
No,
Why is that?
because Texas at the minimum borders 4 other states.
So what? So here, let's say you have a vertex that's connected to 4 others. Just color this.
Wow.
If those 4 vertices are not connected, then, but you're onto something though. Let's take an
Oklahoma,
example.
maybe.
What's that?
Oklahoma, maybe.
Okay, let me take something else. So here's Nevada, let's say, California, let's say Arizona. I think this is Idaho. This is Oregon. I think this is Utah. Okay, so let's consider those states. So what's the graph here? When you build the dual graph, what are you going to have here? Nevada is going to be here. There's going to be California here, Oregon. So these are the states. There's Idaho. And here's the Arizona. I'm kind of crammed here. But this is the dual graph to the US map is going to have like this piece inside of it. All right, it's going to have this piece inside of it. Now, what's the chromatic number of this graph? This graph is just a subgraph of the graph that's dual to the US map. What's its chromatic number of this graph? Let's just try to color it. Yeah, can people help me out?
Can be red.
4.
Yeah, I think it's
Yeah, it's 4 because I can't get away with 3 colors here. So this has to receive the 4th color. Okay, so this graph is small enough so you can test, so you can start checking, and you'll see that you'll have to assign 4 colors to it. So what we know for sure is that the chromatic number of the graph, of the US graph, is going to be bigger than 3. Right? So we can't get away with just 3 colors. We need 4 or more. Okay. So again, the dual graph to a map is always going to be a planar graph. So what we're asking is that what is a chromatic number of this planar graph? In fact, what we'd like to answer today is what is the chromatic number of any planar graph? It's a famous theorem called the graph coloring theorem. Okay, so let me give you a little bit of a background of this theorem. There's a famous one. So in the middle of the 19th century, a cartographer and map maker in England by the name of Guthrie was interested in, he was coloring the maps of the different counties of England. And he noticed that he was able to do this using just 4 colors. So every way he tried, just, tried other places, he never needed 5 or more colors to do this. So he brought up this question with his brother, who was a math student at the time. His brother got interested and brought up the question to one of his professors, who was a guy that you already know, I've met before in a previous run, in a prerequisite of this course, a guy by the name of Augustus De Morgan. Okay, people remember De Morgan from set theory or logic?
Yeah, De Morgan's law.
De Morgan's law. So De Morgan got interested in the problem. He kind of found it intriguing and circulated the problem amongst the mathematicians of the time, including Hamilton. But Hamilton couldn't care less. He didn't think this problem was interesting. But others thought it was interesting and worked on it. A guy by the name of Alfred Kemp was intrigued by this problem and published a proof in 1871, I think, if I'm not mistaken. The problem itself first came up in the 1850s. So Kemp gave a proof, which I will give you his argument today. He thought he proved that you could get away with 4 colors, right? So his proposition was this, what he thought that he proved, that any planar graph, the chromatic number of a planar graph is 4, is exactly 4. Okay, so he thought he proved it, and many mathematicians at the time thought that the proof was correct. It was only 10 years later that it was discovered that there was a flaw in the proof. In fact, the proof was incorrect. And it wasn't until 1970s that the proof of this theorem was found. So it was an open problem for over 100 years. Okay, in the 1970s, 2 mathematicians by the name of Appel and Haken found the proof. However, the proof was a computer proof. It wasn't one of those elegant mathematical proofs, right? So in the mathematical community wasn't all that thrilled with the proof, because the proof reduced to considering so many cases. So many different cases. So the reduction was to like over 1,000 different graphs that had to be checked by a computer. Okay, those special cases. And it's like, this is just not an elegant mathematical proof, but it is a proof nevertheless. So today, by the mathematical community, it is accepted that this theorem is correct. The theorem being that the chromatic number of any planar graph is 4. But there is no elegant mathematical proof even to this day. And I should also mention that the mathematical community itself hasn't given up the existence of such a proof. It just hasn't been found yet. But a proof using computers exists. And that proof has been refined since then. It's been shrunk in size, so it doesn't take like 200 pages to check everything. Fewer special cases are needed today. People are still thinking of that problem. But anyway, I want to give Kemp's argument, though, because it works very well for 6 and 5. So what do I mean by this? What I'd like to prove to you today, that any planar graph whatsoever, has a chromatic number that is at most 6, and you'll help me prove this. Okay, and the argument can be extended to 5. What do I mean by this? What I mean is that any planar graph has a chromatic number that is at most 5. Now, Kemp had these correct. His proof was an inductive proof that helps you to prove those 2 statements. But then he thought that he could extend his argument to proving that any planar graph has a chromatic number of 4. We know it's not going to be 3, right? So we just gave an example of a planar graph with the US example here with this piece of the map that takes 4 colors to color it. So it's going to be greater than 3. So Kemp thought that he had extended his argument to prove that 4 is the chromatic number of any planar graph. He thought he had the proof, but that proof was wrong. However, his proof was correct for 5, and 6. That is, we can prove, and now we're going to prove that any planar graph has a chromatic number at most 6. So let's formulate that theorem. So here's our theorem. So G, the planar connected graph, then the chromatic number of G is at most 6. That's our theorem. That's it. So you can get away with 6 colors. No matter how big the graph is, how many vertices it has, you can properly color it with 6. You never need more than 6 colors. So you can get away with 6 or possibly fewer colors. Okay, so you'll help me prove this, but before we get to the proof of this, we need a little bit of a helper statement. So we're going to go with a little lemma that says that any planar G connected, let's keep it connected although it doesn't have, has a vertex of degree 5 or smaller. So please help me prove this. Proof. It's by contradiction. So please so help me out. You remember we talked about planar cloud graphs last time. We had some results from last time that we just reviewed. So using those results, please help me prove this. So the proof is going to be by contradiction. So what am I assuming if I'm proving this by contradiction? So please, somebody who hasn't participated, please help me out. What do I have to say here? So I'm proving a theorem. If P, then Q. Something implies something else. So I'm saying that if G is a planar graph, then it has a vertex of degree 5 or smaller. Okay.
Don't we start by assuming that the planar graph G has a vertex of 6 or more?
Okay, so no, but you're onto something. Suppose not. Then, so what's the opposite of that statement? It's the con. So what we want to show, what is the negation of the statement? Graph G has at least one vertex of degree 5 or less. What's the negation of that statement?
It has no vertex of degree 5 or less? Okay.
Yeah, then all vertices, every vertex of G is degree 6 or bigger, right? Not just one vertex. So let's keep the logic straight. Okay, so good point. So let's write this down. So degree V1, so you have these vertices. Let's say you have n vertices. Degree V2, so you add those up. Degree Vn, that's going to be, each vertex has degree 6 or more, and I have n vertices. So the sum of those degrees should be greater than 6n. Can I denote the number of vertices by V so that it's consistent with our notation from last time? Number of vertices instead of n, just to be consistent with the notation. You can keep n if you'd like, but number of verts. So we'll say that it's greater than 6V. Okay, so if we assume, suppose to the contrary, that every vertex of G has degree 6 or more, then the sum of all degrees is 6V, right? 6 times the number of vertices. Everybody's on the same page, right? Nobody's arguing with this, right? Before we get to use the G's planar and get to use the results from last time, can I ask you about the handshake lemma? Because that's the lemma that we talked about like day 1 of our graph conversation. When we started the whole discussion about graphs. So on day 1 in that conversation, we talked about the sum of the degrees of any graph. So what's that? What is the sum of all the degrees?
Must equal 2 times the number of edges.
Yeah, so twice the number of edges. Okay, I haven't even used the fact that the graph is planar. I know that twice the number of edges in this graph is going to be the sum of all the degrees. Okay, so we must have that 2e, so let's write it down this way. So 2e is greater than or equal 6b, or e, the number of vertices, is greater than equal 3v. Okay, so this must happen, whether it's given our assumption, right? So the graph is planar. Okay, then if the graph is planar and that if every degree of a graph has degree 6 or more, then the number of its edges is going to be greater than 3 times v. Does anyone object to any of this? Any objection in the courtroom? Any objection to this? Right, that has to be the case. Okay. On the other hand, from last time, by the corollary, really, by Euler's result, what do we have? What did you just tell me about at the start of today's conversation here? At the very beginning, you told me something about the number of edges and the vertices. They're related somehow. So by Euler's results, we have that the number of edges is less than 3d minus 6, right? Didn't you tell me this? And that's correct, because that's what we proved last time, which is a contradiction. What is a contradiction? This and this. These two contradict one another. On the one hand, the number of edges is greater than 3v. On the other hand, the number of edges must be smaller than 3v minus 6. There's no way that can happen, right? Okay. Do people agree that we're on the same page? So the lemma is proof, right? So this completes the proof. QED. Okay. So I don't think people are arguing with this lemma. We just proved that any planar graph must have a vertex that's smaller than 5. Now back to our theorem. Now we want to prove our theorem about planar graphs, that its chromatic number cannot be larger than 6. And we get to use this lemma now that we know. Now, the argument that I'm going to carry out is similar to Kemp's argument from the 1870s. And it's a pretty standard modern inductive argument when it comes to proving facts about graphs. So you pick a graph theory textbook, a graduate textbook, undergraduate textbook, papers on graphs, and this theme recurs all the time. Proof is by induction. Inductive proofs are used pretty frequently. And this one is going to be by induction. And a technique that's frequently employed is to do something with the graph, like remove a vertex from the graph and consider it a smaller graph after you've removed this vertex. Something must be true there. Then you add that vertex back into the graph. And this something, just by adding, you're not changing that something. Therefore, that something had to be true for the original graph. Now, this last couple of vague sentences that I just uttered, we're going to make them very concrete in our example here when we prove this theorem. So with your help, I'm going to, by induction, prove the theorem here at the top of this page. And this is, by the way, practice for the midterm, because you will see problems on induction on the midterm. So this is a good example to practice with. The little wrinkle that I just mentioned, I'll help you with that. But we'll follow the usual guidelines that we've always used that relate to carrying out inductive proofs. So let's prove this. Proof is by induction. Is by induction. Now, you'll say it's all good and well, proof is by induction, but what am I inducting on? I mean, I don't have an end. So what do we do? So the first thing that you will be doing in inductive proofs is formulating the inductive hypothesis. But it's not clear. We don't have a clear inductive hypothesis here. What is n? We want the statement P of n, the proposition that's indexed by n. But what is n? So let me suggest that let n be the number of vertices in the graph. So we're going to carry out an inductive argument on the number of vertices of the graph. So our n in induction of a P of n, the n will be the number of vertices. The number of vertices of G. Right? So you're this that I have to know that for the lemma it was a B. So let's call it N so that we have P of N. So what's the P and F? So help me out now. Help me formulate the inductive hypothesis. How many people are still present here? So let's see. Do people have webcams? Am I just
Yeah, we
speaking?
are
Or
here.
people are here? Are people here?
No, people have webcams.
Okay, so some people are here. So please help me out. So what's the what are we proving? What do we want to? What's the inductive hypothesis?
That P of wait. Never mind.
Yeah, for planar G. So let's do it together. For planar G with n vertices, right? N verts, the chromatic number of G is not larger than 6, is at most 6. This will do as an inductive hypothesis. This is what now we have a proposition that's indexed by n. Now we can talk about induction. So before we couldn't because we didn't have n. It's not clear what they induct on. And I'm suggesting let's induct on the number of vertices. The inductive argument, the induction will be on the number of vertices. Now, I didn't stress this yet, but it may have come up this question in your mind. So first of all, what's the number of vertices that in a graph that we care about? If the graph has like fewer than 5 vertices, and I should have talked about this maybe when we like here, even during the lemma. But do we even care about the graphs that have like 6 or fewer vertices? So what is the fact that we want to establish about those graphs? That we can color the vertices with 6 or fewer colors, right? If the graph has like fewer than 6 vertices, does it even matter? We just have fewer vertices, so we just use fewer than 6 colors, right? So if we have a graph like on, let's say on 6 vertices, and suppose it's like the worst case, that is we're dealing with K6, right? Every pair of vertices are connected in K6. So the chromatic number of that graph of K6, what is the chromatic number of K6?
6.
It is 6, right? The chromatic number of Kn we just talked about is n, exactly n. So for K6, I'll have to use 6 colors for sure, I know that. And it's not, the K6, by the way, is not even planar. And we're assuming that we're talking about planar graphs. So I'm just giving like a complete extreme example. Is just even we don't need to go that far. But the point I'm trying to make is that if a graph has 6 or fewer vertices, we can always use the 6 colors, and we're still within the bounds of what we want to prove. We want to show that we'll never use more than 6 colors to color any planar graph on n vertices. And the number of vertices we care about is 7 or more. Are we on the same page with this? Let's get this base case out of the way. So the base case is not, so we'll take the base case to be like n equals 6. So works, just simply use the 6 colors. Simply use 6 colors. 6 colors. And we've covered the vertices. So that's it. So we only care the graphs that have 6, 7 or more vertices. So let's talk about the inductive step. So what's here in the inductive step? What am I proving? Now, again, we're following the template. So this is practice. This is just another inductive proof. So help me out. Let me separate this.
Should we work for m+1 too?
Right. So let's just be clear. That's the way you'll be writing this stuff down in the exam. So let's just clearly write this down. So in the inductive step, we want to show, so help me out. So what am I showing? Just, you said something that was correct. Just what, if you wouldn't mind, if you repeat it so that I can write it down. So what am I showing?
If base case is working, which is n, in inductive steps, m+1 should be true, should work with m+1 too.
Yeah, so we want to show that, so we use the k for that, right? So to show that pk plus 1 is true, okay, again, so p of n, here's the proposition, p of n. So I want to show that pk plus 1 is true, assuming that p of k is true. So again, it helps to say this, repeat this in words in your mind. What is pk plus 1? So let's repeat this, the sentence. What is pk plus 1? So while I write this down, please somebody say it, if you wouldn't mind.
Well, we want to show that p of k plus 1 is true, assuming that p of k is true for all k greater than or equal to n.
Yes, but what I'm asking, I guess, is that that's it. We agree on that. That's correct. But what is pk plus 1 in words?
Oh, that for planar G with k plus 1 verts, the chromatic number of G is less than or equal to 6.
Yeah, exactly.
n+1.
Yeah, for k
We
plus 1.
switching k with n, right?
Sorry, one more time.
We switching k with n.
M?
With n, because we name
Mhm.
as an n. This is the inductive steps pk plus 1. Yeah, let k be n. Yep.
So let's yeah, for any integer, yes, greater than 7, right? So for that integer, let's take that k plus 1, right? So pk plus 1, as you said. So assuming, so take any graph, take any g with k plus 1 vertices. So we want to show now that this graph, the chromatic number of this graph is at most 6. And we get to use the fact that any whatsoever, any graph on k vertices, planar graph on k vertices, that chromatic number of that graph is at most 6. So now we take any graph on k plus 1 vertices now. Now I want to use this lemma. This lemma says that I have a vertex of degree 5 or smaller, right? So we established that lemma, that separate fact, right? But I do have in this graph on k plus 1 vertices, I do have a vertex of degree 5 or smaller. Do I? I must have it. And let's remove the vertex v of degree 5. Actually, at most 5, but let's see. In the worst case, it has a vertex of degree 5. So it looks something like that. So here's my v. So here I have this larger graph, g, on k plus 1 vertices. It has a vertex v. So this is the graph with k plus 1 verts. It has a vertex v inside. That vertex v is connected to a bunch of possibly other vertices. Okay. But in the worst case, I can't find a vertex whose degree is 5 or smaller. So those other guys, the neighbors of v, in the worst case, all have different colors, right? In the worst case, because they may be all connected to them, so like themselves be connected. Okay, so but in the worst case, what I'm getting is that they all have different colors, right? So in the worst case, so I found a degree, a vertex of degree 5 or smaller. In the worst case, it's 5. And all of those 5 neighbors of v have different colors, right? People agree that's the worst case? Okay, well, towards what end? I guess it maybe not clear why. Okay, so I find that that vertex, and I remove that vertex from G, and remove V from G. So you're left. We're left with a new graph, which is the original G without vertex V. So let's denote it like that. So without this vertex V. So I removed one vertex. How many vertices does that have? So I had K vertices. The inductive hypothesis for this graph, the inductive hypothesis is true for this G on K vertices, right? So I had so just to make sure we're on the same page. Took a graph with K plus 1 vertices. I want arbitrary, just any graph with K plus 1 vertices. I want to show that for that, any graph on K plus 1 vertices, the chromatic number is at most 6. So I take any of those graphs. How do I show that the chromatic number is at most 6? Well, consider first removing a vertex of degree 5, which I know I have in that graph, any graph on K plus 1 vertices, I have such a vertex. So I remove it. I'm left with a graph on K vertices. What's the chromatic number of that graph?
Would it be less than or equal to 6?
Yeah, it's by the inductive hypothesis, the chromatic number of this graph is less than or equal to 6. Now consider, now add, this is at first, the first time you see this kind of proof, which is a very frequent kind of theme that recurs all the time in inductive proofs and graphs. You remove a vertex, then add it back in. Now add V back in to this graph, back in, let's say. When I add this V back into this graph, so I'm back to my original graph with on K plus 1 vertices that I've started. Do I ever need to use more than 6 colors? Would I have to use a new color, the 7th color? Do I have a need for the 7th color? And once you
No.
argue that I have no need for the 7th color, we're done with the proof, with the inductive.
No, because on base case, we already say we can throw it with 6 colors.
What do you mean base case? So base case is here.
Yeah.
Base case is here. So we're done with that. Yes.
For when we add a new when we add back to that vertices, so it's gonna be a k plus 1 again. So we already said on the base case, we said basically on the base case we were talking about a k plus 1. When I compare with the inductive states, it's a little bit complicated. I understand, but I cannot explain. I don't know.
No. The base case, we're not dealing with the base case, right? So the base case is that if I have a graph on 6 vertices, just 6. So base case has to do with this particular case, just 6 vertices. So we're not using the base case here. Maybe when you say base case, you mean the inductive hypothesis. Do you mean the graph on k vertices?
Yeah.
Okay, so let's use that term. So by the inductive hypothesis, the graph on k vertices can be colored with 6 or fewer colors. Okay, so how does it follow now that when I add this vertex v back in, so that I'm back to the graph on k plus 1 vertices, why am I good with the 6 colors alone? Why will I not need the 7th new color to color this graph on k plus 1 vertices? If we argue that this is indeed the case, then we're done with the proof.
You don't need to use more than 6 because well, like in that little dual graph there in the bottom left, you can just make the 6th color the one that's not adjacent to the other 5.
Yeah, so just color V with the 6th color, and that's it. That's exactly right. Because the V has at most 5 neighbors. Even if those 5 neighbors are connected so that they use up 5 colors, V can get the 6th color. So I have no need for the 7th color. This is actually much simpler than the argument, right? Than we just make of it. Does that make sense, though? So what you've just argued, is it clear to everybody that I don't have a need for the 7th color? If the graph on k vertices can be colored with 6 colors, so can the graph on k plus 1 vertices. Because because this vertex that I removed has only 5 neighbors. So with that vertex, in the worst case, I'm using up 6 colors in the vicinity of V and its neighbors, use up only 6 colors. And the rest of the graph using also at most 6 colors. Does that make sense?
Yep.
Okay, so that completes the inductive step then. And so what we've proved in the inductive step, that if any graph on k vertices can be colored with at most 6 colors, then so can be any graph on k plus 1 vertices be colored with at most 6 colors. Everybody agrees. So the inductive step is complete, and therefore our proposition has to be true for any n. Any planar graph on n vertices can be colored with 6 or fewer colors. You will never need 7 colors, no matter how complicated the map looks. The map of the United States, you don't need 7 colors to color it. So you can make this a little bit more stringent. You can say that you need at most 5 colors. That's easy to prove. It's not that difficult. It's along the same lines. It's just the argument is a little bit tricky. Okay, it goes along the same lines. But when you remove this vertex and put it back in, now the problem is that you're using only 5 colors, and this situation has to be refined slightly. Now you can't use a different color for V because you only have a resource of 5 colors. So you need to recolor the entire graph, and in that argument, you sort of have to show how you're recoloring the graph so that you're using 5 colors to color all the vertices of the graph. It's not complicated. You can think through it and just figure it out. But it's just really, we can do it if you're interested. We can talk about this during the office hours, whatever. But Kemp thought that he could extend this to 4 colors. He could come up with a clever way of coloring the graph just using just 4 colors, not 5. So with 5, he could do it fine. But with 4, he thought he did it. It was super, super clever, but there was a flaw in it. And that flaw wasn't discovered for 10 years, and then it was discovered, and then how to fix the flaw wasn't known for another 100 years. And to be quite frank, like even today, there's no elegant mathematical way, just something like this, of showing it. You have to use a computer. Maybe one day. Okay. I think we can stop here. There's plenty of other things we could talk about, but we're not going to talk about them.